Oh, okay, so let's begin by just defining expected value for a discrete random variable. All right, well, we know what this is. We know what this is supposed to be from an intuitive standpoint. It's supposed to be the probability weighted average of the values that the random variable can take on. All right, now we have to clarify something. So let me just write that down. Intuitively, in other words, like the intuition behind the concept of expected value, is that it's supposed to be a kind of like best guess for what the random quantity is, what value it's going to have. So you have a random quantity. Its actual value depends on the experiment. But let's say you don't know what the outcome of the experiment is. But you do know what the possible outcomes are and what their probabilities are. And you know for each outcome what value x hat would have. So if you roll a die and the die shows a 2, then you know that, like, let's say x hat would have the value 57.3. But if the die shows a 5, then let's say the value of x hat is negative 17.35, whatever. Okay? So if you know the outcomes, you know their probabilities, and you know for each outcome what value the random variable has, then you want to take each possible value that the random variable can take on and just multiply it by its probability of occurrence as a weight, and then add those. Because you see, those weights add up to 1, and they're all non-negative, so they can serve as weights in a weighted average. And what that gives you is number that you would use as a best guess, like as a single best estimate of what the random quantity what value it will have. If you have no other information, no more specific information about what the actual outcome is. Let's say before you perform the experiment, that would be the value you would expect the random variable to take on average. Right, another way to say this is that if you perform the same experiment over and over and over again independently, and you calculate the value of x hat in each experiment, and then form a long-run average, you would expect it to be roughly this value. Okay? That's actually a law of probability called the law of large numbers. We're not going to talk about that here, but one can, and it's not even that difficult to prove. All right, anyway, so from an intuitive standpoint, it's supposed to be the probability weighted average of the values x hat can take on. But I have to clarify what I mean by can take on. Because even a discrete random variable, I talked about this at length in my video on discrete random variables. Okay, even a discrete random variable, it's possible that it takes on some value that is not one of those jump discontinuity points of the CDF. It's just that the probability of that happening is 0. Remember, we had this theorem we proved that if I call C the countable set of jump discontinuity points, the probability that the random variable takes a value in C is 1, and therefore the probability that the random variable takes a value outside of C is 0. So it's as unlikely as any event could be, but that doesn't mean it can't happen. So when I say can take on, what I mean is with positive probability. I mean exactly these, where the probability that the random variable takes on exactly that value is like the jump height. And it's only the positive jump heights. So J0 may be excluded from this. J0, remember, could be positive or could be 0. And so if J0 is exactly 0, then that wouldn't be a point of positive mass. But if the jump height is positive, then you have a point of positive mass. And those are the values that x hat can take on with positive probability. So that's really what I mean when I say can take on. I mean to say with positive probability. Okay, well, those values are exactly the a sub n's, which are the jump discontinuity points of the CDF. Remember that by the definition of a discrete random variable, part of the definition is that those jump discontinuity points, those a sub n's, form a discrete set. Okay, and then you multiply that. You have to take, that's one of the values that the random variable can take on. Oh, because remember the pseudo-inverse, when you take that CDF and you reflect it across the diagonal to get the pseudo-inverse, so the domain of that pseudo-inverse is the open interval 0 to 1. But you have to remember that the step heights, the step heights are exactly those a sub n's. And so those are just exactly the values that that step function takes on. This is a picture of the step function x hat. Right? It has various step heights. But the actual heights of those steps are the a sub n's. And so those do represent like the possible values of this thing as a function. All right, anyway, so you take the possible values of that function and you have to weight that by the probability of occurrence, the probability that x hat takes on that value. And let's remember that that is just the jump height, j sub n. And then you'll sum this over all n. Now I claim that we can actually sum this over all integers n. You can let n run all the way through the integers. And let me explain why. You see, remember that we always set a naught equal to 0. If that's not actually a jump discontinuity, then the j0 will just be 0, which means the term a naught j naught will actually just be 0 because j naught is 0. And therefore that term can be included in the sum artificially. The whole term is simply 0, so it makes no contribution to that sum. So you may as well just include it in the sum. It's totally artificial, but it doesn't change anything. Okay? So you see, if 0 is not a true discontinuity point, it's not truly a value that can be taken on with positive probability, it makes no difference. Because that's exactly the case where j naught is 0. And in that case, the term that you're adding is 0 anyway. And it makes no difference, makes no change. So we may as well include it. Okay? And then similarly, remember that if for the original CDF, when we had the original CDF, which was step function, right, whatever it looks like, so if that does hit, let's say, the value 1 and stay 1 forever, so there was like a largest a sub n, but then we artificially added a bunch more to make sure that they go all the way out to plus infinity. And here the jump heights are 0 as well. But again, that just means that when you add the term, if I add this term a n plus 1, j n plus 1, the jump is 0 there, so the whole term is 0. And therefore adding that term is okay. It's harmless. So yeah, I can allow n to just run all the way through the full set of integers in both directions. I may be adding a bunch of 0 terms where the j sub n's are 0. And therefore the entire term is 0. But that doesn't change anything. That doesn't change the actual value of the sum. Okay, so we're going to write the expected value in this way. We'll write the expected value as the sum of an times jn, or you can also write it this way, an times bn times bn minus 1. And n runs through the full set of integers. Right, so just remember that this is, by definition, the nth jump. Also, by definition, bn was f of an. And this was f of an minus 1. Okay. So we can write it very, very explicitly in terms of the CDF. Like this. Okay, where the a sub n's are exactly the set of discontinuity points of f, possibly augmented by adding 0, and also by adding like a sequence of points spaced apart by 1 unit toward the right, if necessary, and also a sequence spaced apart by 1 unit toward the left, all the way to minus infinity, if necessary. Good. So that's the formula for expected value. That's the definition of expected value. But the first theorem I want to prove is that we can represent the expected value. Oh, okay, sorry. I need to say one more thing before I state this theorem. So notice that we can subdivide the terms here into those that are positive and those that are negative. Now there may not be any negative ones, and then they would all be positive or non-negative, right? And similarly, there may be no positive ones, and then they would all be non-positive. That's possible. Because, let me just explain why. See, a naught is 0, right? Now, let's suppose that was actually the maximum discontinuity point already. If that was the maximum discontinuity point, then the CDF would have reached the value 1. And then we would have added a whole bunch of other points, like spaced apart by 1 unit, going out toward plus infinity, artificially, where the jump heights are 0. So this would be A1, this would be A2, A3, right? But you see, J1 is 0, and so that term would be 0. And similarly, J2 would be 0, and so on. So, and then, of course, this term would be 0 simply because A naught is 0. So whether J naught could be 0 or could be positive, but it makes no difference because A naught is 0. So the only terms that would actually appear in the sum would be strictly negative terms. Why strictly negative? Well, A minus 1 is a strictly negative number since it's less than 0. But J minus 1 is positive. So when you multiply these two, you get a negative term. And the same would be true of A minus 2. That term would be negative. So you see that it's possible that there just are no positive terms, but you just have a bunch of 0 terms and then a bunch of negative terms. And of course, it's possible the other way around too, where there are no strictly negative terms either. But the point is that we can always subdivide this big sum here into like the non-negative terms and the non-positive terms. So we would write that this way. Let's say you take all the terms a and jn where n is at least 0, and this whole sum is non-negative. It could be 0. The entire sum could be 0, as it was in this picture, because all of these terms turned out to be 0, and therefore the sum of all of them would have been 0. Okay. And then there's the other terms where the n is strictly negative. So notice I've just taken the integers and split that into two disjoint sets. There's the n that are non-negative, and then there's the n that are strictly negative, and those are two disjoint sets that make up all the integers. Okay, all of these terms are less than or equal to 0, although they may all be 0, and therefore that entire sum may be 0. Okay. Now let's just have a notation for this group of terms here. I'm going to call this the positive part of the expected value, and I'm going to call this one the negative part. Strictly speaking, it doesn't have to be negative, right? It could be 0, but I'll just use those terms because they're evocative terms. So we have like the positive part of the expected value, and then here we have the negative part. Okay, and then the expected value itself is just the sum of those two. Now I'm going to say the following thing. I'm going to say that this expected value is defined in the first place only if both the positive part is like less than plus infinity, and at the same time the negative part is greater than minus infinity. In other words, they're both finite. You see, the positive part is definitely non-negative, but it could be plus infinity, because that series may diverge. You're adding up a bunch of non-negative terms. Now, if infinitely many of those terms are positive, you're adding together an infinite number of positive terms, that could diverge. If it diverges, it would diverge to plus infinity. So it's possible value. But I'm going to require that to be not the case, that should be strictly less than plus infinity. It should be a finite number. And similarly, the negative part could be minus infinity if there's an infinite number of negative terms, strictly negative. But I'm going to require it to not be minus infinity, to be strictly greater. So both of them are finite. And I'm going to say that the expected value is defined only in that case, when these are both finite. And in that case, it's defined as, right, so in this case, when they're both finite, the expected value is defined as the sum of the two. All right, so both parts have to be finite separately. So the reason I'm saying that is because it is possible, it would be a rare thing, but it is possible that maybe this one is plus infinity by itself, and this one is minus infinity in exactly such a way that you get cancellations, and then their sum could be finite. If the positive terms in this one exactly cancel the negative terms in this one, maybe the answer is 0, which is finite. But we don't want to count that, because the fact that it's finite in that case is sort of a coincidence. We just get lucky and we get these cancellations, but nothing should depend on that kind of luck. So it's just not significant. The fact that it's finite in that case is just a dumb luck. It's not any sort of mathematically significant fact. This quantity here only has any mathematical significance in the case where both of these are finite real numbers. And then their sum is a finite real number for good reason, not because of some just piece of luck where you get cancellations. All right, so that's why we have to be very careful about defining things in a meaningful way. Okay, good. Now with that in mind, we're now going to prove this theorem that the expected value, if it exists at all, in other words, if the thing is expectable, can be represented as an integral. It's the integral from 0 to 1 of this function with respect to its variable, which I'm calling omega. Remember, omega is supposed to represent an arbitrary element of this capital omega, which is for us the open interval 0 to 1. So as that runs from 0 to 1, you just integrate this step function. Remember that this is simply a step function, a tame step function. Okay, and I claim that that gives the expected value. But remember, I'm only assuming that this is the case where the expected value exists, in the sense that both, what I mean by this is that both the positive part is less than plus infinity, and the negative part is greater than minus infinity. They're both finite. Okay, good. So that's a nice representation. It's going to help us prove linearity, at least for discrete random variables. All of this is only for discrete random variables so far. It's only at the end we're going to extend our results to other random variables, basically by approximating them by discrete ones. Okay, now, before we prove this, I should mention that this integral has to be interpreted as like an improper integral. What I mean by this integral here is it's really the limit of the integral from epsilon to 1 minus epsilon, as epsilon goes to 0 from above. Okay, you have to interpret it that way because notice that the function x hat is undefined at 0 and also undefined at 1. Those are not in the domain of the function because the domain is just the open interval, 0 to 1. So you can integrate from, let's say, epsilon to 1 minus epsilon and then take the limit. All right? Good. So anyway, the proof goes something like this. We're going to just look initially at the integral from b naught to 1. Of this function. And again, you have to interpret that as an appropriate limit. Okay. Now notice that b naught could actually could be 0. So you might have to have a limit at both ends. Or if b naught is strictly between 0 and 1, then you would just have a limit at this upper end. You would integrate up to 1 minus epsilon and then take the limit. Okay, so I'll just operate under the assumption that that is understood. Okay? Anyway, so you see that what you're going to get, because it's a step function, its graph just consists of a bunch of horizontal line segments between consecutive b's. And so the integral can be calculated very easily because for a step function, the integral is the area under the curve. And by the way, notice that, okay, I should draw this picture. Let's say b naught happens to be here. So the corresponding value of a is a naught, but a naught is 0. So if I go to b1, then the corresponding height would be a1, and that's greater than a0. a0 is exactly 0. a1 is greater than that. It means that the height at b1 is positive. Well, okay, let me correct myself a little bit. Remember that the filled-in circles are actually the lower circles. So it would actually look something more like that. But the point is that the function is non-negative between b naught and 1. On this interval between b naught and 1, the function x hat is entirely non-negative. And then in this interval, b naught to 0, the function would be non-positive. Like the function x hat would go down from there. All right, that's why I'm using b naught as a split point to split up the integral. Sorry, to split up the interval between 0 and 1. Because basically to the right of b naught, the function x hat is non-negative in height. And then to the left of b naught, the function is like non-positive in height. Okay, but anyway, you're just taking the area under these little bars. Right? So if the next one, for instance, looks like this, we would then take the area under that next little bar and so on. And we're just adding up all of those areas. Because that's what the Riemann integral is. It's the area under the function. Okay, so here's what that is going to look like. The height of this first bar is like a1. In general, you're going to have a sub n as the height. And then what's the horizontal width of that bar? Well, it would be something like b2 minus b1. In general, it would be bn plus 1 minus bn. Oh, sorry, whoops, I guess I made a little mistake here. Actually, the picture is a bit wrong here. This bar would have been at 0 height, going up to b naught. the next bar would have been at the height A1. And so on. Okay. So let me just fix this picture here. So I have the, oops. I have this blue rectangle, and I have that blue rectangle, and I have that. And I'm just adding up all those rectangle areas. Okay, does that make sense? Yes, yes. Okay, so like, let me just make a little comment here. This bar here, this step, doesn't really have to be at height 0. It could be height below 0, which is what would happen if 0 is sort of artificially included. If this 0 has to be artificially included, it means that there wasn't really a discontinuity there of the original capital F. And in that case, this bar actually would be down below that. But this first bar here that's extending between B0 and B1, that definitely is like strictly positive. The height level is A1, which is strictly greater than A0. Okay, anyway, yeah, so that I have to correct this, and this is actually just Bn minus 1. In other words, Jn. So we're going to get the sum of An, Jn, but it's not for all n, it's only for n starting at 1. Right, because the very first term there corresponds to the area of this rectangle here. Let me draw that in sort of solid blue. The very first term would be that solid blue rectangle. The next term would be like that next rectangle. Now that first term was A1 times B1 minus B0. In other words, A1, J1. So that's the first term. Okay, therefore n begins at 1. However, we can artificially include the n equals 0 term. And it doesn't change anything because remember that A0 is 0 by the way we set things up. So therefore A0 times J0 is also 0. And that's true whether J0 is positive or whether J0 is 0. Because the A0 is 0. That's the advantage in setting things up the way we did. Okay, so I can artificially include the n equals 0 term in that sum, and now you see that the answer is just exactly like the positive part of the expected value. So that's this integral here. Now, I was a little careless in this derivation in terms of like the improper limit of 1, and possibly even if B0 happens to be 0, you could even have an improper limit at the lower limit. So I was careless in treating those here. How would that actually work out? Okay, well, if I put in an artificial upper limit here of 1 minus epsilon, then there's only going to be a finite number of those bars, these blue rectangles. There's just a finite number of those between B0 and that point, and this point here. That's by the tameness property. Because remember that between epsilon and 1 minus epsilon, there's only a finite number of those B values. So there's only going to be a finite number of those bars. Okay, and then we can just add up those. Actually, the very last bar is going to only be partially included, right? Because like you might have this bar here, let's say in solid blue, but then the very next one might get cut off because you have this gray line right in the middle. So you're just going to get a partial rectangle. But it's still a rectangle. See, if you take a rectangle and you just cut off part of it, the resulting bit is still a rectangle. So yeah, you just have a sum of like finitely many rectangle areas. Okay? And so that's going to give you this integral up to 1 minus epsilon as the upper limit. But then if you let epsilon go to 0 from above, you're just including more and more bars. And in other words, you're just including more and more terms of this series. If that's an infinite series, the more bars you include, the more terms you're going to include. So instead of cutting it off at some arbitrary cutoff point, you're just including more and more terms. Now, the limit of a series, as you include more and more terms, is just the full sum of that series. So you see, as you take the limit of this, epsilon going to 0, you get the full improper integral up to 1. And as you take the limit of this, as epsilon goes to 0, you're just getting more and more terms, basically partial sums of that series. And you're taking the limit of those partial sums. Well, the limit of the partial sums is just the full series, by definition of a series. So yeah, on this side here, this limit just gives you the full range of integration, except it's going to be from b0 up to 1. Okay? And then on this side here, as you take the limit, you're just including more and more terms, more and more n values. And then you'll just get the full sum. You'll get the full sum where you include all the non-negative n values. But of course, because the two limits are equal, you'll get this equation. Right? So I was a little careless in treating the improper nature of the integral at 1, but nevertheless, it's still a correct calculation. It's easy to fix, and just be a little bit more careful about the nature of these limits. Okay, and you get the correct theorem. Okay, well, that's just the non-negative part. Obviously, the same calculation applies to the non-positive, the negative part. Basically, the negative part is going to come out to be, so by definition, it's this, where n is negative, but that's just going to come out to be the integral from 0 up to b0 of the same function, for the same exact reasons. So basically, the positive part came out to be the integral from b0 up to 1. Okay, also notice that since I assumed that these are both finite, it tells me that the improper integrals converge. See, up to now, I didn't actually know if like this limit here is a finite limit. How do I know that that limit actually has a finite value? Okay, well, by the discussion we just did here, this limit, as epsilon goes to 0, is equal to the sum of this series. And since I assume that that series converges, right, by assuming that this is a finite real number, that's why I'm like, I need this assumption here, that the expected value exists. This is an expectable discrete random variable. The expectability tells us that this series here converges, because the positive part is finite. And that also tells us that this limit here, the improper integral, it's like improper at 1, but it's convergent. It's a convergent improper integral. Okay, so actually these are finite real numbers. Okay, and then finally, like the actual expected value is just the sum of those two. So you're basically integrating from 0 to b0, and then again from b0 to 1. And it's the same integrand and the same dummy variable. And we know that that just gives us this integral here. Okay, so that gives us the correct formula. That's the proof of the theorem. Good. Well, now we get something quite nice as a corollary of this, which is that if, let's say, x and y are both expectable, discrete random variables, then their sum is also an expectable discrete random variable. Okay, we know that it's discrete already. We proved that. But the new piece of information is that their sum is also expectable. Okay, and the expected value of the sum is just exactly the sum of the two expected values. That's a key piece of the linearity theory. Remember that the goal of this whole excursion we're doing right now is to give you some justification for the linearity property of expectation. Now, this is only for discrete roundabouts. We haven't gotten the full linearity just yet, but at least we've gotten a piece of it now. Okay, and the proof is easy.